Hello, I'm here in normal video land to correct this Lenz's law problem caused by the learning glass. Definitely not my fault, definitely the learning glass's fault. In fact, I think there should be a little warning on the learning glass box that says, if you're trying to teach Lenz's law, do not use this setup at all. Okay, here we go. Refresher on Lenz's law, just a little reminder. Lenz's law says that if you have a conductive loop, all right, it doesn't like change. In fact, it hates change so much that if you change the magnetic flux moving through that loop, okay, then it'll induce its own current designed to counter that flux. Remember, currents create magnetic fields. So if the loop doesn't like the new flux that it has, right, then it's totally allowed to create its own current to counteract that flux. All right, so we'll see what that looks like in a second. First of all, I just want to remind you that there's actually three ways flux can change, right? So flux is actually equal to BA cosine theta. Flux can change by changing the magnetic field. It could change by changing the area through which, you know, the flux is moving through. Like you could squeeze that or expand that, right? Or you could be changing the angle. In other words, you could be rotating this loop inside the field, or rotating the field itself, okay? So be on the lookout for any one of these, because if any one of these changed, then the flux changes, and then you have an induced EMF. Feels weird to be using shock again. Okay, so let's take a look at this first example, okay? The first example for Lenz's law here is this one that says that you have a magnetic field going into the board like this, right? And you have a little loop of wire inside that, right? Little magnetic field, okay? And then we decide over here to squeeze that loop so that it's like this. Okay, so remember, if flux is equal to B A cosine theta, then which of these three variables is changing from here to here? Well, it's the area. And what's changing? Well, there's less flux now, right? There's less area. Area is going down, so the flux is going down, okay? That means that this loop is upset. It panics. It doesn't know what to do, so it actually now wants to induce a current that has more flux going into the board. So the original flux is going in, right? These little X's mean in. I can actually, my end of the board is the same as your end of the board now, which makes life easier. And so now this loop wants to make a flux that has more in. So it's like it was before, right? But what direction gives you more in? Well, so I want it to be in. I want this to be in here, right? So if the magnetic field is going to be in here, that means the current on this side must be going up, and it must be going down on this side. So that would be a clockwise current. Okay, so just by merely squeezing this, suddenly you're inducing a clockwise current, because a clockwise current will give you more magnetic field in here. Remember, it kind of looks like this. There's like these magnetic field lines that loop around and go in. So it'll go in here, and then on the outside, it'll be coming out at you. But that doesn't matter, because what's on the outside doesn't determine the flux here. The flux is only what's through the inside of this area. Okay? All right, that's example number one. Example number two has a slightly different situation. In this example, we have magnetic field coming out like this. So all these magnetic field lines are coming towards you, towards both of us, and I have a little loop here that's being yanked out of this magnetic field, okay? Now, if this loop is being yanked out of the magnetic field, and let's say, you know, now it's down here, right? Let's say it's down here, then in that case, you have no magnetic flux anymore, and it wants that old flux back, right? It's like, what the flux? I want my old flux back. So you have now a desire to recreate this magnetic flux coming out again. Well, what direction current will give you a magnetic flux coming out? Well, I want it to go in on the outside, come back around and be out on the inside. That's going to be a current that goes in this direction. That would be an induced current in this direction, which would be counterclockwise. Okay? A counterclockwise current will give you a magnetic flux coming out on the inside so that you get the same flux that you used to have. All right? All right. I think there's another example here. Okay, in this other example, it looks something like this. You have this long kind of like, thing to hold the shape. And you have a set of wires like this, right? And then here is a battery with a little switch, okay? And then on the other side, the wiring kind of goes like this, right? And comes back around like this, and you have this little meter here, okay? And the question is, will it be going from the positive to the negative side or the negative to the positive side? What is the direction that current's going to be going through this little meter once we close this switch? Okay, so the first thing we have to ask ourselves is, what flux does it have originally? And the bottom line is, it has no flux. This gives no flux whatsoever, okay? So in that case, it is enjoying having no magnetic field moving through it. But the second I close this, right, now I have a magnetic field that is coming, so this is the positive end, so I have a current this direction, right? Okay, a current in this direction means that the magnetic field is going to wrap around this wire and come out this way, right? Inside this tube, it'll come out. So you have this net magnetic field in this direction, that then curls around, comes back, right? Curls around, comes back, right? And you have little arrows here, right? And there's all these field lines, does the same thing, right? So now suddenly you have this flux moving this way that it doesn't like because before it had nothing. So it wants to oppose, it wants to get rid of this new flux, so it wants to induce a magnetic field in this direction to oppose this new flux. Well, what direction does this coil need to go to have a magnetic field in this direction? Well, if my current's going down in front, up and down here, right? Then that's going to be a magnetic field that points this way, this way, this way, this way. So in other words, if I have an induced current that does this, right, then I have a current ultimately that comes down this way and then moves over here from right to left. Okay? All right. That is the essence of Lenz's law. You just look at the original flux, you see what this original circuit or loop liked, you look at the new flux, you see how it's changed, and then you induce whatever current is required to get you back to what you had before. Basically, that's how it works. That's all the examples for this video, but we're going to return at the end for a little bit more practice with Lenz's law. See you there.